The laser, light amplification by simulated emission of radiation. Its development in 1960 still stands as one of the major breakthroughs of the 20th century. But the groundwork for the laser took place in the early 1950s with the Maser, an Air Force Office of Scientific Research supported invention by the Nobel Prize-winning Dr. Charles Townes. Today, AFOSR-supported engineers and scientists around the world continue to push the boundaries of scientific discovery, developing and employing cutting-edge laser technologies to solve real-world problems.
So these ultra-fast lasers with their high repetition rates and their incredibly short pulses open up a whole new world of combustion chemistry and physics that we just couldn't study in the past. Start in the lab, work in the test cell, ultimately impact these weapon systems on the flight line and in the air.
At Eglin Air Force Base in Florida, HP3 Center of Excellence researchers are using laser diagnostics for more effective weapons testing.
I design experiments and direct experiments and then analyze the results of what we call shock experiments, which are experiments that we do at this facility where we measure material properties at really high pressures, the kind of pressures that materials might see when they're subjected to an explosion or to a high-speed impact.
Lasers are effective in weapons testing because of their inherent ability to provide extremely precise measurements or feedback on explosive effects. They accomplish this in a manner that is safe and minimizes the loss of sophisticated equipment.
And by basically continuously improving our material models and our understanding of material behavior, we increase the chance that things work the way we hope them to, and we, of course, decrease the chance of expensive problems with fielded weapon systems.
In the Combustion and Laser Diagnostics Research Complex at Ohio's Wright-Patterson Air Force Base, scientists are using picosecond and femtosecond lasers for innovations to combustion chemistry and physics, a body of research that is leading to more efficient jet engines. Pico and femtosecond lasers emit fraction of a second light pulses at repetition rates in the billions per second.
And what we do here basically is we shoot laser beams into jet engines, which sounds like an awful lot of fun. And the motivation for that is to study the fundamental chemistry and physics that takes place in those combustion processes to improve the performance of the individual components. And ultimately, we would like to see these lasers applied to full-blown engines to make measurements in systems like the B-2, the F-22, the Joint Strike Fighter, to name just a few, where we can actually solve real problems for the warfighter. So we go all the way from basic research funded by AFOSR, where we're uncovering the new fundamental nuggets of knowledge in combustion chemistry and physics, to making the airplanes fly better for our boys and girls in the air.
With the support of AFOSR, the speed, power, flexibility, and application of lasers continue to break barriers.
We are standing in a laboratory that is producing attosecond pulses that will be used for molecular dynamics investigations. This technology is quite a high risk, and a lot of agencies would not really support the long-term effort that would be needed to build up such a laboratory. But AFOSR has been quite visionary in this respect, in taking risks and giving us the opportunity to do these new technologies.
These technologies are just a few examples of the cutting-edge AFOSR research that would not be possible without the advent of the laser and the groundwork laid by Dr. Townes. And additional revolutionary possibilities are on the horizon. What many consider fantasy or science fiction, AFOSR makes real. Learn more about U.S. Air Force-funded laser projects by visiting our websites, www.afrl.af.mil and www.afosr.af.mil. Like us on Facebook, watch us on YouTube, or follow us on Twitter.